SCAREcrow, Sentinel Conservation via Aerial Reconnaissance and Escort.
Hey guys, welcome back to another video. In this video we're going to go over the architecture of SCAREcrow. If you navigate to our wiki within the github.com link, which I'll have down in the description below, you'll see a couple different pages on the right hand side. Right now we're on the home page, but if you go ahead and click on System Architecture, you can follow along as I describe the various diagrams, what they mean, and the components of the system. So at a high level, we have three components that we've created of our 4-component system. We have the controller interface / controller. We have the base station. We have the agent, which is on board the drone, and we have the autopilot. Our system consists of the agent, the base station, and the controller interface / controller. And then of course we have the autopilot on the drone that we talk to. So the way this is split up essentially is the base station runs on a computer. Doesn't really matter where it runs as long as it's close enough so the latency isn't terribly high. The controller runs on a computer that has access to a camera for watching the field where the animals may be encroaching in. And then the agent code runs on our NavQ board provided by NXP. The NavQ board connects over serial to the autopilot. It talks Mavlink via the Mav SDK to the autopilot. The communication between the agent and the base station and the controller interface in the base station is Wi-Fi or IP. The base station acts as a authentication layer as well as a router. Theoretically, in our system, it's been designed to be able to have multiple agents and multiple controllers. And as new controllers or new agents join the system, the base station matches up controllers with agents. So we could have, maximum we can have around 255 nodes in the system. So 254 divided by 2, if we had an even number of agents and controllers, would be the number of agents and controllers we could have. So 254 combined agent and controllers, in addition to one base station. The controller interface is responsible for monitoring the field, identifying the threats, and then commanding its agents or agent via the base station to scare the animals out of the field. So as the controller interface here senses animals in the field, it will send set point messages to the base station destined for its agent that it owns. And then the base station, authenticating that this controller owns this agent, will then forward the packet for the set position onto the agent. At which point the agent will respond based on the state machine, based on which state it's in within the state machine, which we'll show below. Ultimately, the set points will be converted into off-board commands, and those will be sent over Mavlink to the autopilot, causing the drone to go to that point in space. As the controller notices the animals moving within the field, it will change the position at which it wants to send the agent to. So the agent will continually be following the position. However, once the animal leaves the field and the controller stops sending set points, the agent will have a timeout period where once it doesn't receive set points after a certain amount of time, it will then return back to where it launched from, land, and wait for new commands. As mentioned above, we have the agent code. Essentially, the agent has 2 parts currently, and then we have some ideas for some future improvements. So currently we are listening for drone movement commands and then setting the target location. And then the state machine, which I'll show next, actually looks at the target location, checks the staleness of it, and if it's not stale, meaning it's a new command, the state machine will then go through the process of taking off, going to the point, and continually going to the point until the set point becomes stale, at which point it'll return to launch like I had mentioned before. Some future improvements would be using the onboard camera, the Coral camera on the NavQ board to actually watch for animals off of the drone and then better locate the animal relative to the drone, so the drone can track that animal directly. And while it's tracking the animal, it can fuse the location of the animal with the location that the controller is sending it. So one, it can pick out the right animal, and two, it can have a hybrid approach to tracking that position and or animal. As far as the state machine goes, we'll go ahead and look at that next. So the agent state machine essentially first checks for the staleness of the target. If the target's not stale, then it goes into targeting mode. Or rather, it wants to get to targeting mode. So if it wants to get to targeting mode and we're in the wait state, it's going to unlock and then set the home location to the current location, plus 2 meters above, and then change to takeoff mode. It'll come back up. The next iteration of the state machine will go back through the check. It won't be in wait state anymore. It'll be in takeoff state, at which point it will set the takeoff altitude, send a takeoff command, and then wait to get to the takeoff location. So as it waits to get to the takeoff location, it continues in this loop like so. Once it's at the takeoff location, it will change to targeting mode, which will then bring it down to this branch. As it's in targeting mode, it will be changing and updating the set point mode, the set point that we sent to the offboard mode controller. Upon the first iteration, the offboard mode will be turned on, and every iteration after that will just be updating the position that the offboard mode is sending to the autopilot. Once the agent code realizes that the position set point is stale, meaning there's been a decent amount of time, in this case 2 seconds, since the last set point has been received, it will come over here and check what state it's in. Of course, at this point we know we're in targeting state, so then it will change its state to return to launch. And then again, because it has a stale state, it'll come down here, and it's not in targeting state anymore, it's in return to launch state, which means it will set offboard mode to home location, and then wait to get home, and just continually check if it's at home. Once it's at home, it will change to land state, which will then come up here, position still being stale, will change to land state, and the agent code will command land via the map SDK. Then as it commands land, it will continually check like so. And then once the drone has landed, it will disarm, and then it will go back to the wait state, at which it does this. In the wait state, it will check for the staleness of the message still, and when the staleness of the message is no longer stale, it will eventually change to takeoff mode and continue down the path that we already described. Next up, we have the controller code. The controller consists of 2 components. We have the convolutional neural net portion, and then we have the reinforcement learning portion. The convolutional neural net portion is pulling frames from the RGB camera, scanning for animals, and then based on a calibration process, it is locating the animal from the monocular image and getting an XYZ or an XY location out in a field. For this process, it assumes a flat plane. So we calibrate the camera and are able to, by the height of the pixel, judge the depth of the animal, and by the width of the pixel, judge the X position of the camera. So we get Y from height, X from width, and we're able to locate the animal into the scene. At the same time, the Python interface for the controller is subscribing to drone locations. And then every time it gets the drone location, it updates the scene with where the agent or drone is. Then at some frequency, the reinforcement learning pipeline will essentially run over the scene and generate a command for the drone to target. And of course, if it doesn't see any animals in the scene, it will not create a position. And then as we saw above, the position will make its way through the base station and to the agent. The base station is fairly simple. It's mostly asynchronous threads. So we have a thread for receiving hellos, which is the message type that any new node in the system sends to the base station to join the system. This is how the base station prints out the join message and actually assigns an ID to that node. We have one for receiving agent move commands, which are the commands that come out of this block here. Essentially, it does some verification against its list of agents and controllers and the correlated list of controllers who own agents that it creates. And if everything is kosher, it forwards to the target agent. Similarly, we have a receive agent location. It again verifies the source is in fact an agent that it has previously connected to its system, and then it forwards it to all of the known controllers in the system. And lastly, we have a loop here that iterates over all the controllers, picks out the best controller, and iterates over the agents to assign the best controller. This is how the controller when it joins, or the agent when it joins, is automatically assigned a controller or an agent, depending on who it is. This portion will need to be changed in the future. When we have multiple drones, there will need to be a metric for who is the best controller. For now, it's picking the newest controller to match up to the agents. And so that is our architecture. Next, we're going to get into the architecture of the machine learning portion of the code, specifically the way that Adam has architected the system on the Python side of things to have multiple different types of algorithms that can both be that can all be called up independently when running this algorithm, as well as a way to essentially test his system independent of the overall system. So without further ado, we'll hop over to C-Line and we'll get into that project. So for starters, I want to draw your attention to the left-hand side here where we have the project set up. You'll notice it has the entire SCAREcrow project. Adam's code is a module within the controller folder as a Git submodule that references to his Git repository. Inside of his submodule, he has his package installation setup information as well as the actual code. You'll have to reference the documentation on our wiki page for how to get his system set up properly. But as far as the architecture goes, you essentially have two folders and then some files here. We have a controllers folder where all of the controllers are stored, and then we have the envs folder where various things for the environment are stored. Outside of that, we have the main and the params. The params file allows you to set various parameters for the project. You'll notice that you can change the algorithm that's being run here. You have the hardware option. If you set this to false, it will test only his project. If you set it to true, it will require the entire system being spun up and running. And then there's a few other parameters that we won't get into great detail at this point. Everything is launched from the main. So you'll notice there's a lot of red here. C-Line doesn't quite understand the mapping of these files. So there is some issues, but actually the project runs. So there's some more issues we need to figure out, but for now, we'll just ignore that. So as you can see here, he has a concept of episodes. Essentially, when the environment is spun up, it's reset at the beginning of the episode, and then it creates the different types of algorithms, and then it tells them to play. The environment itself has a couple different interface functions. So we have the reset, which you saw above, and we have the step, and as well as the render. So every time the step gets called, it essentially passes the action from the keyboard, or from in the human instance, it's the keyboard, but in the reinforcement learning instance, it's the action from the output of the reinforcement learning algorithm. The action is passed down to the SCAREcrow, which is a SCAREcrow 2D, which we find here. The action inside of here is passed to the defender by a move command, which causes the agent to actually move, and then the system's able to continue on and draw the agent moving, and then each frame this gets called essentially. One of the inheritance uses here is if you're in hardware mode, it spins up a defender that's a hardware defender, and if you're not in hardware mode, it spins up a defender that's just the virtual defender. And so essentially all a defender is essentially a way to move the icon on the game board that he has. And then if you're in the mode for hardware, it actually communicates via the move command and via the controller interface. It sends a move command to the agent, and then when the controller interface receives a new position for the agent, it actually calls this callback, which allows us to update the agent's position on the game map. So the move command here asynchronously changes the update based on the agent reporting its location, whereas the move command here synchronously updates the location because this is the class that would be used when you're in the closed system, versus this is the class that gets used when you're using the entire integrated system. And then one last thing to go over is the uh, class here that we have for the actual human-based controls. So as you remember, we called the play function from the main after selecting the human or the rule-based or the Q learning approach. The play gets called, and it is a blocking call that just essentially loops and listens for human input, which comes from here. That comes from the keyboard. And then it calls the step on the environment, which, like we showed, this is the environment. Step calls the SCAREcrow, which is a SCAREcrow 2D. That step goes into the action call. So you see we say SCAREcrow.action given the action. And then the action gets passed down to the defender as a move call, and then depending on which defender it is, it performs that specific defender's move. After that, it renders, and then it goes back to the top and does it all again. So as you can see, the implementation for having different types of controller types is not all that complex. The complexity comes in how the controller itself implements the algorithm. So I won't get too much into detail of it, but as you can see with the Q-learning one, there's a bit more code here, and basically it involves some training here. And then he has got a couple different models that he's experimenting with that are in addition to the rule-based and the Q-based. So here's the rule-based, and as you can see, it's a whole bunch of if statements to decide where the drone should be relative to the hog in the field. And so there you have it, our full system design. If you enjoyed this video, go ahead and hit the like button down below. Also subscribe to catch more videos about SCAREcrow. In addition to that, if you have any questions, leave a comment down below and we'll try to get to it as quick as possible. Otherwise, have a nice day and thanks for watching.